Imagine drilling 4 kilometers straight down into the earth, through layers of rock that have not seen daylight for hundreds of millions of years, to reach water hotter than 400 degrees Fahrenheit. Now imagine doing that without breaking your drill bit, without triggering an earthquake, and without burning $100 million on a dry well. That is the daily reality of geothermal energy. And in the last few years, machine learning has quietly become the most important new tool in the entire industry. I'm going to walk you through how, across 30 slides, in the next half hour. We'll cover the data, the models, the cutting-edge research, and the real projects where this is already paying off. If you're an engineer, a data scientist, an investor, or just curious about how AI is being applied to clean energy, this one is for you. Let's get into it. Here's our roadmap. We'll start with why geothermal needs machine learning at all, because that framing changes everything that follows. Then we'll go through the 4 big domains where ML is being deployed today. Subsurface characterization, basically seeing through rock, drilling and operations, making the well itself faster and safer, production and reservoir management, squeezing more energy out of the field once it's running. And finally, the cutting-edge architectures, the stuff that's still in research papers, but moving fast, physics-informed networks, graph neural networks, transformers, generative models. We'll close with 2 real case studies, a results comparison, and an honest reality check on what doesn't work yet. If you only watch part of this video, the case studies near the end are where the rubber hits the road. But the foundation matters. Let's start there. Quick context. Geothermal energy is unique among renewables for one reason. It's firm. The wind doesn't always blow, the sun doesn't always shine, but the inside of the planet is at 6,000 degrees Celsius, and it isn't cooling off anytime soon. A well-run geothermal plant runs at over 90% capacity factor, 24 hours a day, 7 days a week. And yet, geothermal is less than 1% of global electricity. Less than 1%. Why? Look at the third stat. Drilling routinely consumes around half of a project's capital cost, and in some hard rock projects, it's even more. Every well is a multi-million-dollar bet on what's underneath. And the fourth stat is the punchline. Subsurface uncertainty is enormous. We are making expensive decisions with sparse data, deep targets, and limited ability to see what we're aiming at. That uncertainty, that is exactly the gap machine learning is built to close. Before we talk about neural networks, let's be fair to the classical tools. Geothermal engineers have used physics-based simulators for 50 years, and they work. But the subsurface is noisy, sparse, and nonlinear. And those 3 words break a lot of classical methods. Look at the right-hand column. Sparse, expensive labels. You might have 10 wells in a field, each one drilled over months at huge cost. Multimodal signals. You're fusing seismic waves, electrical resistivity, thermal gradients, brine chemistry. Heavy noise and uncertainty. Heterogeneous rock. Fractures you can't see. Layers that aren't where the model said they'd be. And finally, strongly coupled physics, heat, fluid flow, rock mechanics, and geochemistry all interacting at once, on timescales from seconds to decades. A traditional simulator handles each of these one at a time, with simplifying assumptions. Machine learning doesn't replace that, but it fills the gaps where the assumptions break. So where does ML actually plug in? 4 places, and these 4 are going to structure the rest of this video. Stage 1, exploration. Where do we drill? Which prospects are most likely to host a productive reservoir? ML helps you rank them before you spend the first dollar on a rig. Stage 2, drilling. Once you've decided to drill, how do you do it faster, with fewer broken tools and fewer surprises? Stage 3, production. The well's online, the plant's running. How do you get the maximum lifetime energy out of the resource without damaging it? Stage 4, monitoring. Seismic risk, equipment health, scaling, corrosion, catching the problem at minute 1 instead of month 6. Each stage produces a completely different kind of data and uses a different ML toolbox. Let's walk through them. Part 1. Subsurface characterization, or as I like to think of it, seeing through kilometers of rock with neural networks. This is the most mature application of ML in geothermal today, mostly because the oil and gas industry has been throwing deep learning at seismic data for over a decade. Geothermal has been able to inherit a lot of that work and adapt it to its own needs. The goal here is simple to state and brutal to execute. You want to turn a soup of geophysical, geochemical, and well log signals into a coherent three-dimensional model of where the heat, the fluids, and the fractures actually live. Look at the diagram. On the left, your inputs, seismic cubes, well logs, geochemistry, magnetotelluric, and gravity data. On the right, your outputs, lithology maps, permeability fields, the temperature distribution, fracture density. In the middle, convolutional networks, random forests, gradient-boosted trees. The exact architecture matters less than what's happening conceptually. Why ML? Because the relationship between, say, seismic reflectivity and the local permeability of fractured granite is not something you can write down in a clean equation. There's no closed-form formula for it. There are messy, non-linear, location-specific patterns, and that is precisely what neural networks are good at finding when you give them enough labeled examples. Let's zoom in on one specific application: seismic interpretation. A seismic survey produces these enormous three-dimensional volumes of acoustic data, terabytes of it. Geophysicists have traditionally sat in dark rooms with workstations, manually picking out faults and horizons by hand. It takes weeks. It's tedious. And different humans pick differently. Convolutional neural networks, especially the UNet architecture you may know from medical imaging, now match expert geophysicists on this work at a tiny fraction of the time. Three-dimensional CNNs do volumetric segmentation. Self-supervised pre-training lets you take advantage of the unlabeled seismic data, which there's mountains of. And in the last couple of years, transformer-based architectures with attention have pushed performance further by capturing long-range structural context. Basically, faults that span the whole survey. But, and this is important, the geoscientist is still in the loop. The model proposes, the human disposes. That hybrid workflow is where the real productivity gain is. Here's a more focused example: predicting the temperature you'll find at depth before you drill. Look at the chart. The x-axis is essentially a depth temperature index from your input features. The y-axis is the predicted temperature. The orange dots are a classical model. You can see the scatter. The model misses by 10 or 20 degrees Celsius pretty regularly. The teal dots are an ML prediction trained on the same inputs. Tighter, more accurate, lower variance. How do they do it? Inputs include depth, lithology, well log curves, geochemistry of nearby springs, and regional heat flow. Models are gradient boosting, XGBoost, light GBM, random forests, sometimes simple multi-layer perceptrons. The outputs are full temperature versus depth profiles with uncertainty bounds attached. And here's why it matters in dollars. This is what lets a developer rank prospects before committing to a $10 million exploration well. You'd risk the bet. That's a very direct, very tangible impact. If you take one number away from this video, take this one. Drilling can be over half the total cost of a geothermal project. In hot dry rock projects, sometimes more. So even a small percentage gain in drilling efficiency translates into massive economics. This is where ML earns its keep. Fastest. Rate of penetration is exactly what it sounds like. How fast the bit is grinding down through rock, measured in meters per hour. Now, ROP isn't just a function of how hard you push. There are three big inputs. Set points, the things the driller controls, like weight on bit, RPM, and mud flow rate. Formation properties, how hard, abrasive, or fractured the rock is right now. And bit state, how worn the bit is, what type it is, how it's been performing. You feed all that into a surrogate model, usually a neural network or gradient boosting, that learns the mapping from current conditions plus my action to expected ROP. Then you wrap a Bayesian optimizer around it that searches for the best set points in real time. Reported gains in the literature are in the 10 to 30% range, plus reductions in drilling dysfunction, things like stick-slip vibration, washouts, twist-offs. Lower cost per meter, faster wells, fewer trips out of the hole. The economics are very, very real. This chart is the kind of thing you'd see on a real-time drilling dashboard. The orange line is a predicted bit health risk score. The gray line is the alarm threshold. Notice what happens around hour 15. The score starts climbing steadily. By hour 23, it's about to cross the alarm threshold. That tells the driller, probably you should pull the bit and inspect it before something expensive breaks down hole. How does this work? Step 1. Sensors stream MWD and LWD data. Vibration on 3 axes, torque, RPM, ROP, mud flow, standpipe pressure. Step 2. Featurize. Rolling statistics, frequency domain features, cross-channel correlations. Step 3. Score. A hybrid model, often an autoencoder for unsupervised drift detection combined with an LSTM that's been trained on labeled failure events. Step 4. Recommend an action. The whole thing runs at the rig. Sub-second latency. That's a different operational regime than offline analysis, and it's where drilling ML is heading. Same idea, applied to the most expensive failure mode in drilling, stuck pipe. A stuck pipe incident, where the drill string gets jammed downhole and you can't move it, typically costs over $1 million to resolve. Sometimes much more. Sometimes the pipe is lost permanently and you have to sidetrack the well. The good news, stuck pipe almost never happens out of nowhere. There are warning signs. Torque starts climbing, pickup weight starts changing, mud return chemistry shifts. A trained sequence model, a 1D CNN feeding into an LSTM, is a common architecture, learns the normal rhythm of the wellbore for that specific operation, and flags drift seconds to minutes before a human operator would notice. The pipeline is on the right. Stream the data, featurize it, score it with the model, act on the result. Auto-alert the rig crew, surface the recommended action, sometimes just pump more mud, slow down the trip, and you've avoided $1 million headache. Part 3. Production and reservoir management. Now we're past drilling. The well is online. The plant is generating power. This is where the long-term economics are decided. Over the decades, a geothermal field operates. And it's where the most subtle, long-horizon ML problems live. Look at the chart. The black line is measured power output in megawatts over 12 months. The gray line is what a classical decline curve, the standard industry baseline, would have predicted. It drops too fast. The orange line is an LSTM, a recurrent neural network. It tracks the actual measurements much more closely. Why? Because reservoirs don't decline along a clean exponential curve. Injection events happen. Operational changes. The operator opens or closes a valve, swaps a turbine, drills a new well nearby. All of that creates structure in the production time series that a fixed decline equation can't capture. Sequence models are the right tool. LSTMs and GRUs handle long lags. An injection event might affect production 6 months later. Temporal convolutional networks are easier to train on long horizons. Transformers let you model dependencies across many wells and many variables simultaneously. And hybrid physics plus neural network models, where the network learns the residual of a physical decline curve, often beat both pure approaches. Now we're getting more advanced. Reinforcement learning. Reservoirs are not static, they're dynamic. The operator can adjust injection rates daily, change well bottom hole pressures, route flow through different wells. Each of those decisions has consequences that play out over months or years. RL turns this into a control problem. The agent, a neural network, trained with algorithms like PPO or SAC, learns a policy. A policy is just a function that takes the current state of the reservoir and outputs the next action. The environment, on the right, is a reservoir simulator, or, increasingly, a learned digital twin of the field. The agent takes an action, the environment evolves, returns a reward and a new state, the agent learns. Repeat for millions of simulated years. By the end, you have a policy that handles long horizon trade-offs no static optimizer can. Look at the bottom. That's the reward function. Energy produced, minus pumping cost, minus scaling risk, minus thermal breakthrough penalty. The RL agent is balancing all of those, all the time. That is genuinely beyond what humans can do by hand. 3 quiet killers of geothermal economics. Each gets its own ML treatment. Mineral scaling. Geothermal brines are loaded with dissolved silica and calcium. As the fluid cools and depressurizes, that stuff precipitates out, directly inside your pipes, your heat exchangers, your turbines. Gradient boosting models, trained on brine chemistry plus operational history, predict scaling weeks before it becomes a problem. Corrosion. Hydrogen sulfide and carbon dioxide are common in geothermal fluids, and they eat metal. Time series classifiers fed with chemistry and flow data predict corrosion rate, so you can schedule maintenance before something fails. Induced seismicity. This one's the most sensitive. When you inject high-pressure fluid into rock, you can trigger small earthquakes, usually micro events nobody feels, but occasionally larger ones that cause real damage. Bayesian models combined with spatial graph neural networks estimate the expected event rate as a function of your injection plan before you press the button. That's a regulatory and social license requirement now in many jurisdictions, not a nice-to-have. Part 4. Architectures. Everything up to now is in production somewhere. The next 4 slides are where research is moving, what I expect to be standard practice in geothermal 3 years from now, but isn't yet. PINs. Physics-informed neural networks. This is one of the most exciting ideas of the last few years. Standard neural networks have one problem in scientific applications. They don't know any physics. You can train them on data, but if your data is sparse, and remember, in geothermal it always is, the network will happily learn predictions that violate basic conservation laws. Mass appears, energy disappears, things fly off the rails outside the training distribution. PINs fix this by putting the physics directly into the loss function. Look at the formula on the left. The total loss has 3 terms. L data, match the observations, like a normal network. L physics, the residual of the governing partial differential equations, evaluated by automatic differentiation through the network's own outputs. And LBC, boundary conditions. The network is forced to satisfy the physics, even where you have no data. The benefits, on the right. PINs generalize from very few wells, because physics regularizes the network. They make inverse modeling natural. You can recover unknown parameters like permeability or thermal conductivity. The downsides? They're hard to train. The losses don't always balance well, and they're computationally hungry. But the trajectory is up and to the right. Graph neural networks. This is a perspective shift more than a new algorithm. The insight, a geothermal field is a graph. Wells are nodes. Fractures and pressure communication paths are edges. Injectors push fluid into the system. Producers pull it out. Some wells are well connected to each other. Some are essentially isolated. A standard ML model treats each well as a row in a spreadsheet. It loses the structure. A GNN keeps it. The model learns by passing messages along the edges. Each well's prediction depends on its neighbors, and theirs on theirs. The use cases are the things that have been hardest in classical reservoir engineering. Inter-well connectivity, which injectors actually feed which producers. Pressure and temperature propagation across the field. Joint forecasting. Instead of predicting each well's output independently, you predict the whole field at once, and the predictions stay consistent. Watch this space. It's early, but the results are very promising. Transformers. Yes, the same architecture behind every large language model you've heard of. They're showing up in geothermal too, and for good reason. Self-attention scales gracefully. You can feed in thousands of time steps and dozens of variables in a single forward pass. Years of operational history across the whole field. Multivariate attention lets every well look at every other well at every previous time. Long context. You can model dependencies that span the entire history of the project. Pre-train on a large corpus of unlabeled time series. Fine-tune for your specific field. That workflow is rapidly becoming the norm. And probabilistic outputs. Quantile heads give you uncertainty bands, not just point predictions. There's even talk of a foundation model for the subsurface, pre-trained on global seismic and well log corpora, then fine-tuned per project. We'll come back to that idea on slide 29. Generative models. The 4th pillar. The hardest thing about geothermal isn't predicting. It's quantifying uncertainty. A single well doesn't tell you what the rest of the reservoir looks like, but you have to make decisions anyway. Generative models give you ensembles of plausible alternatives, and you reason over the ensemble. For kinds, variational autoencoders learn a compact latent space of subsurface scenarios, useful for fast Monte Carlo. GNNs generate photorealistic synthetic geological models, handy for training data augmentation. Diffusion models, which you may know from image generation, are increasingly being conditioned on well data and seismic constraints to produce geologically realistic reservoir realizations. And neural surrogates, fast-learn stand-ins for finite volume simulators, sometimes 1,000 times faster than the original. Stitch all of this together and you get what people now call a digital twin, a living, learning, statistical model of your reservoir that you can query, optimize against, and stress test. That's the long-term direction this whole field is heading. Part 5. Let's get out of theory and into the field. 2 case studies, then a comparative results slide, then an honest reality check. Case study: high enthalpy fields, Iceland. Iceland, the poster child of high enthalpy geothermal. The Helishii-class plant generates around 300 megawatts of electricity equivalent, plus large amounts of district heating. It taps a steam-dominated, 2-phase reservoir at very high temperatures. And the operational bottleneck, after decades of development, is no longer drilling. It's silica scaling and managing reinjection. Look at the right side. 4 ml applications that have been demonstrated in published Icelandic work. Silica scaling early warning, using gradient boosting on brine chemistry plus production data. Production decline forecasting where LSTM ensembles outperform classical ARP's decline curves. Reinjection scheduling using reinforcement learning agents that balance immediate power output against long-term thermal breakthrough, meaning they avoid cooling down the producers prematurely. And microseismicity nowcasting, tracking small injection-induced events in real time and adjusting injection accordingly. This is mature, deployed work, not vaporware. Case study: enhanced geothermal systems, EGS. Now to a much more speculative and much more exciting frontier. Enhanced geothermal systems. Conventional geothermal needs 3 ingredients: heat, water, and permeable rock. Most of the planet has the first. Almost none of it has all 3 together. EGS aims to engineer the missing pieces, drill into hot, dry rock, hydraulically stimulate it to create fractures, and circulate water through the artificial reservoir. The U.S. Department of Energy's Forge project in Utah is the flagship test bed. Target reservoir temperature, 220 degrees Celsius. Around 2.5 kilometers of granite basement. ML is involved in 3 places. Microseismic ML, real-time location and moment magnitude estimation of stimulation events. Fracture mapping, graph models infer flow paths between events. Stimulation control, RL adjusts injection in near real time to grow fractures along desired directions, safely. If EGS works at scale, geothermal stops being a regional resource and becomes a global one. ML is on the critical path. Time to put numbers on it. This chart shows error reduction or performance gain reported in the literature across 5 major task categories, comparing ML to a classical baseline. Anomaly detection, 45% improvement. Temperature prediction, 38%. Lithology classification, 27%. Production forecasting, 22%. ROP optimization, 18%. Now, read this with care. The numbers vary widely by site, by dataset, and by what baseline you're comparing against. The biggest gains are usually where the baseline was simplistic. Out-of-distribution wells that don't look like the training set, often erase the gain. And in academic papers, there's always a bit of a publication bias toward the successes. The honest takeaway: the gains are real, but they aren't free. You need a real, tuned, classical baseline to compare against, not a strawman. Otherwise, you're not measuring ML against physics. You're measuring ML against laziness. Time to put numbers on it. This chart shows error reduction or performance gain reported in the literature across 5 major task categories, comparing ML to a classical baseline. Anomaly detection, 45% improvement. Temperature prediction, 38%. Lithology classification, 27%. Production forecasting, 22%. ROP optimization, 18%. Now, read this with care. The numbers vary widely by site, by dataset, and by what baseline you're comparing against. The biggest gains are usually where the baseline was simplistic. Out-of-distribution wells that don't look like the training set, often erase the gain. And in academic papers, there's always a bit of a publication bias toward the successes. The honest takeaway: the gains are real, but they aren't free. You need a real, tuned, classical baseline to compare against, not a strawman. Otherwise, you're not measuring ML against physics. You're measuring ML against laziness. If you're starting a geothermal ML project, For the engineers and data scientists watching, 5 practical recommendations if you're starting work in this space. 1. Start with the question, not the model. Pick one expensive decision your team makes today, not a vague, we have data, let's do AI, and design the dataset around it. 2. Build the data pipeline first. Cleaning, aligning timestamps across sensors, normalizing units, sensor curation, that eats 80% of the work. Don't underestimate it. 3. Always have a strong physical baseline. Decline curves, analytical heat flow models, drilling specific energy. Beat the baseline, don't ignore it. If you can't beat it, you're not adding value. 4. Embed physics where you can. PNN losses, monotonic constraints, conservation checks at inference. Hybrid models almost always beat pure black box models in this domain. 5. Quantify uncertainty. Prediction intervals, ensembles, calibration plots. A point prediction in geothermal without a confidence interval is not just incomplete, it's actively misleading. Looking ahead. For trajectories, I'm watching closely. Foundation models for the subsurface. Pre-trained on global seismic and well-logged corpora, fine-tuned per project. The ImageNet moment of geosciences is probably within the next 2 or 3 years. Closed-loop autonomous drilling. Edge ML at the rig, taking sub-second control decisions, supervised by humans rather than driven by them. The first fully autonomous geothermal well in a controlled setting is, I guess, less than 5 years out. ML-accelerated EGS at scale. Cheaper, faster, safer engineered reservoirs unlock geothermal in places that don't have the geology naturally, which means almost everywhere on Earth. And finally, open data and shared benchmarks. The Department of Energy, the International Energy Agency, academic consortia, all building what could become the ImageNet of the subsurface. Common datasets, common benchmarks, faster collective progress. The line at the bottom captures my honest view. The subsurface is becoming legible. The only question is who reads it first. That's the tour. Earth's heat, decoded by AI. If you got value from this, the most useful thing you can do is hit subscribe. That's how the algorithm tells me what to make next. Drop a comment with the topic you want covered in more depth. Maybe a deep dive into pins, maybe a tutorial on building a production forecasting model from scratch, maybe a longer look at induced seismicity. I'll read every one. And if you want the papers and the code I referenced, links are in the description. Geothermal is one of the most underrated clean energy stories of the next decade. Machine learning is one of the reasons that's changing. If you want to be on the inside of where those two things meet, stick around. Thanks for watching. I'll see you in the next one.